All right, so today for the Journal Club run by TMT, we're going to be talking about this paper about peripherally inspired e-skins. And this is a paper I like a lot. It came out a few years ago, 2019, from the National University of Singapore, Benjamin PKT lab. And I think it's, kind of the concepts in it are pretty simple, but I think are the most kind of cutting edge that I've seen in the field of e-skins. So I'm excited to talk to you guys about it today. To introduce myself, I'm Iskarous. I'm in the Tissue Course Lab working on sensory feedback for upper limb prostheses. So the reason I'm interested in this, of course, is that for our sensory feedback, we start by measuring stimuli in the environment through e-skins. And so this is kind of one step in our sensory feedback process. So something that we follow very, very closely. So yeah, very excited to share this, and for everyone around, feel free to jump in anytime with questions. I don't know every single detail of these papers very well, but I'll try my best, and we can see what we can get out of it. I don't know how many of you guys got a chance to actually look at the paper before. It's okay if you didn't, but just to, okay, so we're coming in mostly fresh. Cool. Makes my job. All right, so the architecture for their electronic skin, they call it the asynchronously coded electronic skin. And so just to kind of give background on what they're trying to do here, right? So as you can imagine, touch sensing is very important for robotic and prosthetic systems because we use our touch sensing for manipulation of objects, to communicate with others, to have awareness of our environment. And so, when we want to control robotics, having that sensory loop to help us understand what's going on and to help us, tell the hand what to do is very critical. And so what we want for a system like this is we want a system which has very high resolution, meaning that we have thousands of sensing units in the hand or the arm or whatever. And we also want it to be fast. And so in this case, we're looking at biological inspiration. And so we're talking about millisecond precision because that's kind of the scale at which we're able to gather tactile information and respond to the environment. So those are kind of the high level ideas that we want really high resolution sensing at a very fast speed. And obviously those are ideals. And so there are always trade-offs between these. Other kind of maybe secondary concerns is that when we're talking about touch, you're interacting with the environment, and so the environment can be dangerous. So you want a touch system that's pretty robust to damage, and won't fail, because of one point of damage. And in designing these sensor systems, we want it to be pretty flexible for lots of different configurations. So those are kind of like the high level ideals that we want for a sensor. And so kind of what they're showing here at the top part of the figure is they're trying to make an analogy between biological and artificial touch. So on the right side, the purple, biological touch, you have all these receptors in the skin, and they create spiking activity that then travels through your nerve, and then you have some sort of perception in your somatosensory cortex to understand what you're touching, right? And so they're thinking of this in the same way in the artificial sense, where you have your robotic finger or your e-skin with sensors on it, and that information is bundled up with your asynchronous coding, and then you have some sort of artificial intelligence or processing afterwards to understand what all this tactile data is. Okay, so that's kind of the high level motivation behind all this. So you have a very traditional way to make sensors, right, is you create some sort of transducer, measure, sensor to measure tactile information, and then you hook up that wire from your sensor to your processor. And so you have a sensor that has a certain resolution, it can, have a certain range that it can measure, and then it transmits that data over a wire to your. Okay, so this is obviously very straightforward. It's fast because your limitation is the amount of information that your one sensor produces, and it's directly wired to your processor. And so, it's a really fast system. But it's not gonna work because you wanna have thousands of these sensors, so you're gonna have a big wiring problem. Where do you fit all these wires, in your sensing system? Like if you have a finger with hundreds of sensors, where do all those wires go? And then you go to your processor. You wanna have a processor with hundreds or thousands of pins connecting to these external sensors. So it's a good starting point, but when you're trying to create scalable systems, that's not enough. Okay, so that's first generation. The second generation of sensors, the traditional way you do it is through some sort of sensing array. So you create horizontal and vertical lines, and where those lines meet, you have a sensing flow. And so if you have, let's say, a 100 by 100 array, you have 10,000 sensors, but you have reduced the wiring problem. Instead of having 10,000 wires, you have 200 wires, right? 100 along one row and 100 along the columns. Okay, so when you create this mesh array grid type configuration, this helps with your wiring, but then it messes up your speed, because to read from your sensors, you go through them serially, you do time division multiplexing. So if I have 100,000 sensors, I'm going to take my time and say, I'm going to devote some time to read from sensor 1, sensor 2, sensor 3, all the way through 100,000 in a serial order, and then I go to the beginning, right? So you're scanning through all the sensors. And so that is the trade-off that you're giving. You're giving up, you're using less wiring, but then you're serializing things. And so that has kind of been I would say the second generation approach that most people take is create arrays, but then again, when you try to scale up to big scales, then thousands of sensors, it's not going to be good enough because of the time to do multiplexing. So to kind of make that a little more clear, again, if you have 100,000 sensors and you want to get effectively 1 kilohertz sampling rate, which is 1 millisecond, right? That means you're going to need 100 megahertz sampling rate at your processor to go through all those sensors, right? And so you need really high compute to be able to bring in all that data. Okay, so that's kind of the state of sensing generally. There's a lot more to it than that, of course. There's ways to do like compressive sampling and other things like that. But this, I think, kind of illustrates the base level.
Yeah. So you're also sensing multiple things, right? It's could you like sensing the temperature, or you could be sensing data.
Yes, yes. So that's another good point, right? So I've just been talking about one modality, but you might want to do another modality. Like in this paper, they do touch and temperature, which are both like tactile and of nature. Yeah, so then you are making your problem even worse, right? Okay, so that's kind of where things traditionally have started, going from one extreme of 1 wire per sensor to another extreme of creating these arrays, but then having to do time division multiplexing. Okay, so now going to biology, what do we find when we look at biology? We find that in biology, our sensing is asynchronous or event-based, meaning that you only send signals when something happens, right? And so there's sparsity that comes along with sending signals in an event-based manner, right? So the way I've been recounting it so far is that you're scanning every single time, every second or millisecond or whatever it is, and so you're getting a lot of redundant information. So if you only send the information that is important, events, so when there is a contact event, that will help make your problem a lot more manageable. Okay, so when you move to this asynchronous encoding, you're going to sparsify the data that you're sending, and it becomes more manageable. Okay, and then to help with the wiring problem, one ideal thing that you could do is if your data is sparse enough, you can actually channel all your data on one single wire. And if you have a single wire, this brings lots of benefits that we're going to talk about: robustness, simplicity, and reconfigurability. So we're going to show examples of those a few minutes. Okay, so how does the ACEs actually work? If we look at the bottom part of this figure, you see the encoding of the ACEs system. So in A, what you have is each sensor is like consider a like receptor, okay? That's just the terminology that they use. And what happens is when an event is triggered by that receptor, it sends out a series of spikes, okay? And this is kind of where all the math comes in that they do, that if you read the appendix, you can see a little bit more about it. But basically, each sensor has a unique sequence or signature of pulses, okay? And so they've designed it in this specific case that their pulses, their signature consists of 10 pulses over a 1 millisecond time period, okay? And each of those pulses is 100 nanoseconds, meaning that within 1 millisecond, there are 10,000 spots where you could have those 100 nanosecond pulses. So you have all those available combinations of 10 pulses within 1 millisecond, and each sensor has its unique signature, okay? And so whenever that sensor is triggered, it sends us a pulse, a sequence of 10 pulses at a very specific time, okay? So you have here sensors 1 through 5, those pink, blue, yellow, green, purple, right? Each of those has its own unique pulse. But what is shown in B is that each receptor has its own pulse, but you collect all of those signals together on one wire. And so in B, what you're seeing is the sum of all the components of the left, okay? And so you've taken each receptor, combined it into one, on one conductor, and then you get to your computer, and that's where you do the decoding, right? And so the decoding, basically the way it looks through the signal, is basically it gets a sequence of pulses, and it knows all the pulse signatures, and it's able to it's looking for how well does the sequence I'm seeing match up with signatures I know, right? And basically they do like a correlation measure. And once the correlation is above some threshold, then we say, okay, I'm pretty sure that this pulse came from that sensor. And so then you can figure out what time each sensor ate that, right? And so what's being shown between A and C is that if you look at the initiation point, let's say on the purple, the top line, you are able to detect that event in C at the same time, right? So here, right, you're not keeping the sequence of pulses. You don't care about that anymore. The pulses were just there as an identifier of the sensor. You only want to know when does the event happen. So between A and C, what you see is that you're able to tell every time the pulse is generated. So for the purple, it's like halfway through. For the green, it's a little bit earlier. For yellow, we never get an event. For blue, there's 2 of them, right? And so by doing this basically correlation-based metric and reaching the threshold, you're able to decode the output. So again, just to summarize, the magic of this is every single sensor has its own unique pulse signature. They all get combined on one conductor, and then at your computer or your decoder or whatever, you're able to then take that combined signal and separate it out into its individual components. So it's very, very, very simple kind of concept.
So orthogonal multiplexing that they use in telecom, in the telecommunication system, they divide the signals on different frequency bands that shove more data through one line.
Exactly. Right.
And it's all happening in real time, right?
Definitely A and B is happening in real time. The decoder, I'm not 100% sure. I don't remember if they reported on.
Wouldn't that be the whole point though?
Yeah, so like, right, if you have some sort of closed loop system, yes.
They have like some op-amp circuit in this figure.
Yes, so I'm gonna go to that one next.
Like real time.
Well, so the op-amp is, well, I guess we can start.
So how many channels can you effectively decode with this encoding?
Yeah, so, good question. So they make certain assumptions, right? So they say that, right, they chose 10 pulses in 1 millisecond and 100 nanosecond pulse. So they have calculations in the appendix which show the possibilities. And they also have assumptions about how much traffic you're getting, meaning how many of these sensors do we think will be transmitting simultaneously. So using the scheme that they have here, they calculate that they can do 130 1,000 sensors with, like 60 nanosecond precision. It's really, really good. So and they came up with that number. Well, that's the number they calculated as a result, and they were like 130,000 should be more than enough to cover like a full body e-scan. Now, I don't know, we have to dig in more into details in terms of, again, what's the assumption about how many sensors are active at once, because the more you have active at once, the harder it is to separate out the signal based on the correlation. So you have a lot more, noise, signal to noise that you need to deal with. So we can look at the assumptions, but that's what they designed the system for with this encoding scheme, 130,000 at 60 nanoseconds. The examples that they show, I think the biggest system that they actually show running was 240. So.
And the decoding is like a probabilistic decoding, that they would have a confidence level that, or.
Yeah, exactly. Yeah.
So the more the channels, the less the confidence will be.
Yeah, well, I think the more the channels, the less confidence would be. So as I said, they set some sort of threshold. So in the case where you expect there to be more traffic, you might set the threshold higher so that you are more, you have more specificity, but then it might take a little longer to get the answer, or it might mean that, there might be other, deconvolution issues that you run into. But yeah, so it's assuming some sort of sparsity again, and assuming some sort of threshold that you just kind of, they measure like this threshold is good enough, that gives you really good, doesn't give you false positives, doesn't give you false negatives, you can calculate the specificity. Cool. All right, so let's go to the receptor itself. It's actually a very simple circuit, and which is why I really like it. So basically, the blue box represents one receptor, and basically what you have is you can have whatever sensor input you want, but usually it's modeled as like a resistive divider. So you have your variable resistance sensor, and that gives you a reading that goes through some really simple microcontroller on the ADC. And then in your microcontroller, that's where you have the actual, basically, behavior of the receptor programmed. And so I'll show you an example of that on the next slide. But basically, in the microcontroller, that's where you get basically events are triggered, and out from the microcontroller is when you send that spike signature, pulse signature. And so that's basically the circuitry for the receptor. The capacitor that's after the microcontroller, that's basically a low frequency blocking capacitor. And the idea is if you're sending pulses, you want to make sure that you send the high frequency information and block the DC. And so that's why that capacitor is there, to get rid of the DC offset. And then you basically have that circuit repeated many, many times, however many receptors you have, and you have one op amp. Basically, it's just a inverting summing amplifier that just combines everything together. And so the output from the amplifier is the one that goes to your computer where you do the decoding, the fourth oscilloscope or whatever. Yeah, so very, very simple circuit. I mean, in terms of the actual components of this is like, electronics 101, 102 level. So it's pretty cool that, it's not really, the complexity isn't in the hardware side, it's all in the architecture. These other plots, basically, so W is referring to the number of pulses in the signature. So they tried out how changing the number of pulses in the signature affects different properties. And so there you see like false positive, false negative, and talking about the number of overlapping signatures. So that's what we're talking about in terms of the overall amount of activity. So it doesn't really matter too much unless you really want to dive into it, like these bottom figures. But basically they're just characterizing for different versions of the pulse signatures how the system behaves. But for the purpose of what they do here, it's all using pulses. Yes.
So if I understand correctly, so if the sensor goes above some threshold, right, so this fires that particular signature for that particular receptor.
That's a way that you can program it, right? So right now, all we've said is that you're getting analog readings from your sensor. It's going into your microcontroller, and then your microcontroller is going to make a decision about when to send out the pulses. And you can program in the microcontroller different schemes for when you want to send out the pulses, right? So we're going to see an example of that. All right, so that's what's being shown here. So here they're modeling. Well, let's start with the tactile ones. Okay, so the tactile ones, there are two main tactile receptors in biology: the slowly adapting and rapidly or fast adapting. They call it here. And so the slowly adapting receptor, basically the firing rate of that mechanoreceptor is proportional to the static force. So higher force, more spikes; lower force, less spikes. And then the rapidly or fast adapting receptor basically is like a derivative. So when you have big changes in the force, then you get spiking activity, right? And so then going back to what you're saying, right? The microcontroller is where you encode that. So the microcontroller, you get your ADC readings, and you say, if my ADC reading is certain amplitude, then I give spikes at this rate. That's the SA encoding. In the case of the fast adapting, you're saying, if my current reading is a certain amount bigger than my previous reading, then I give spikes, right? And so it's at the microcontroller level where you're determining the response. So what they're showing here is in A, they're just calling kind of a diagram here that you could have different receptors that are sending different types of signals, and then you decode them however you want. So in B, what they're showing is that it's kind of hard. Maybe I should have zoomed in a little bit, but basically this is a contact experiment where basically I think they're like touching something with the sensor. They're applying a load, or like either they're measuring something from a load cell or holding something. But basically the load cell is your ground truth about your force. Okay, and so it's like this red line. And the blue colors, let's see if you see I'm trying to see if I can, seems I can. But anyway, what's that?
You pick up those three dots and get a pointer.
Yeah, the problem is I'm sharing, I only have one screen, so I'm sharing it in a kind of weird way. Anyway, it's fine. So, so the blue spikes, so the top is showing you a reconstruction of the force based off of the output spikes. And then the bottom is showing you the output spikes that are actually created. So if you look at the SA line, you see those blue spikes. Those blue spikes, as we said, are giving you spike rate proportional to the force. And so what you show is that if you reconstruct the force signal based on the blue spikes, you get a really good match between your load cell and your slowly adapting receptors. That's when we're talking about really slow timescale forces. And that's why they show the timescale in that case, that bar is like 250 milliseconds. So that's on the left. But then there's this break point, and you see that there's this prick, and the prick is at a much smaller time scale. So in the case of the prick, your slowly adapting is not giving you good representation because you're encoding through the spike rate, the amplitude of force, so it misses those moments. But your fast adapting is better able to reconstruct the quick stimuli. So in the fast adapting, one thing to notice is that there are two colors of spikes. They have that orange color, which is representing increase in your input signal, and they have that the light blue, aquamarine blue, that's a decrease in the signal. And so the fast is telling you when your signal is increasing and when it's decreasing, and so you can kind of get really fast events that way. And so the point they're showing is that having these two encoding schemes, one is really good for low frequency force, and one is good for high frequency force. And that's kind of the whole point of the scheme.
The fast adapting one is actually better than the real nerves, like the real touch receptors, because the fast adapting ones don't have a negative.
Yes, you're right. Yes. So in this case, they cheated. They made a negative fast adapting, which doesn't exist, right? Okay, so that's what's shown in B, basically, is that this and I guess this kind of highlights exactly the maybe philosophy of papers like this where they're doing biologically inspired, but they're not like, they don't care necessarily about having high fidelity to biology. It's just kind of a starting point, but it doesn't need to match everywhere. If they can cheat and make things better, then they don't. Because they care about performance, right? It's engineering. Okay, so so in B, they're basically showing with your slowly adapting and your fast adapting, one is better at reconstructing your static force, and one is able to pick up the fast events. And then in C, what they're showing is they have an example of a finger, and that finger has pressure sensors on the top, and then it has a row of temperature sensors on the bottom. And these temperature sensors are encoded in a way that as the temperature increases, the spike rate decreases. And so what they're showing in D is basically, I think they grab like a cup, like a hot mug of coffee. And so there's the grasp event. So before the grasp event, you have some baseline firing rate for your temperature and your pressure. When you grasp afterwards, your pressure activity goes up because there's more force, and your temperature activity goes down because the temperature is higher, which in this case is encoded as lower spiking rate. So that's kind of what's shown in the raster in D. And then E is kind of basically giving you overall measurement of activity from the individual receptors to detect again, pressure or temperature. Okay, so this is an example they gave of modeling tactile events through slowly adapting, fast adapting, and doing multimodal sensing with this temperature sensor.
This is shockingly familiar to how the vestibular system seems to encode motion.
What way?
With the, well, there's the type 2 and the type 1 paracells and afferents. One of them is responsible to acceleration, the other one's just kind of
Position.
Yeah, so position.
Yeah, it's kind of interesting. I mean, it's not surprising, I guess, but at the end of the day, all these systems end up being like it's like physics.
Yeah.
It's like you want some baseline measurement and the derivative of the measurement and the derivative of that measurement. It's like, and then so it's whatever level of their derivative that gives you the information you want, right? So for motor, I think they care maybe to the third derivative, they care about jerk. Anyway.
Same vision.
Same vision.
Yeah.
You have your like
Edge detectors,
right.
and then like the derivative of edge is like curvature.
Right.
And then like the more advanced than that, then you have like three-dimensional curvature. But then there's also the slow changing stuff, which is like color and shading cues and stuff like that, which are the slow adapting analog and visual system.
Yeah, okay. So so this is kind of an example of ways you can encode things, and then they go through a bunch of like application examples. So here they have they do slip detection. And so the idea with the slip detection is that you have this array, and here they're looking at the fast adapting events because those are corresponding to the changes. And so you're looking at the fast adapting events that are happening across this array over a period of time, right? And so you would imagine if something is slipping downwards, that you're going to get activity in the top sensors first, and then later it's going to be the middle sensors and then the bottom sensors, right? And so there's like a clear direction of motion. And so that's kind of the calculation that they do is they calculate these local movement estimates of like the vector, around each sensor, and then they calculate an overall local movement estimate. So that's kind of a way that they detect object movement. And so then in B and C, they're showing two different examples. Basically in B, they're showing like this big object that's slipping. Again, you have your load cell is like your ground truth indicator. And then you have an estimate of the movement based off of your sensors in red or based off of a camera. That's again another ground truth. And kind of the main point they want to make is that this asynchronous encoding ends up letting you detect the motion faster than a camera-based system. So that's, again, a big object. And then on the right, they're doing the same thing, but they're doing it with like this really small pin. And they're just saying that it's also very sensitive to that. And so the interesting thing with that one, if you look at the red, it's like kind of messy. And so what you see is that basically it's clearly able to detect slippage, but there's a lot of noise there that it's not maybe able to like get the trajectory as well. So, okay, so that's one application. Another application here is for grading pitch classification. And so the idea of gradings basically, you have some sort of texture and they have little gradings, so they're like little bumps, and the bumps have different spacings and different heights or whatever. Okay, so one problem generally with classification of gradings is that it's pretty easy to do if you know the speed at which you're moving across those gradients, right? So if you have a nice robotic system, you know it's moving 50 millimeters per second, then you can basically compute basically the space between the gradings by using your velocity as part of the calculation. But the reality is that you don't want to be relying on knowledge of the velocity because the velocity can change and you don't know how reliable it is. And so they were able to do this speed invariant pitch classification. And so basically what they do is they collect this data from, again, you see the FA events, and you get this spectrogram, and they do some sort of, what do I have here? They have some sort of way to estimate the tangential speed, but like over time, not just the overall tangential speed.
They use a neural network.
Yeah, so they do, I think it's like some sort of convolutional network to eventually do grading classification. And what they're showing in C is that they can do decent classification of the gradings just based off of the spectrograms. But if you supplement the spectrograms with the estimated or calculated speed, then your classification increases as well. So, yeah. And kind of the main point again in D, they're showing this system is better because if you were to do this with some sort of frame-based sensing, ours ends up using way less data to get to the same point.
So do you know for both this figure and the previous figure, they used convolutional neural nets. Do you know if they're like pre-designed ones for a similar purpose, or do they like train their own? Like,
I looked in the methods.
find it in the methods.
Yeah, it says they just use a multi-layer perceptron. So it's just like a very generic classifier probably. So I think they take the spectrum, they bin it, and then they put that through their.
Theoretically, like you mentioned, that it depends on the velocity or the speed with which you move across the gradient.
Yeah.
So there theoretically, at least there will be multiple pitch and velocity combinations, which will give you exactly the same output, right?
Yes. Yeah.
So it's impossible, it's like an ill-posed problem to distinguish between these combinations.
Yeah, so this is something I'm interested in, and I don't know that I have a good answer, but I think you are able to, I think from the spectrogram data, you can actually distinguish, like you said, if you have a grading of 4 millimeters, like distance 4 millimeters and 2 millimeters, and then your velocity is 2x, theoretically it should be the same signal and time. But I think there is something about the spectrogram that they're able to distinguish between. Now, it might be that it has something to do with like shear forces, that you don't end up getting the same signal from moving at velocity 20 millimeters per second versus 40 millimeters per second. So it might be something about the mechanics rather than like the idealized situation. So maybe in the idealized realm, you're right, it's ill-posed, but in reality, these other forces actually make it doable. I don't know for sure, that's just like my.
Maybe if you're like using different time constants of adaptation
Yeah,
and combine them, they'll come up with different signatures for.
could be, yeah. I need to look into it more, but I think it's possible. Okay.
If you like blindfold a human, and like do that, like present two different like spatial frequencies of texture at different speeds that theoretically would be the same, like can they tell? Like,
Yeah.
Yeah,
So you are able to identify the textures independent of the speed, basically, that you can tell that it's different feature sizes. What's the method for that? I don't know exactly, but I know that that's possible. And again, that might be because of the shear forces and some other things that are complicating it. So, yeah. Okay. Another application that they have here, so this is another sensor, I think, what is it? It's like 96 sensors or something in this circular array, and they just did a variety of classification tasks. So in B and C, they're showing that they're able to classify between these three different shapes, and they have one set of those shapes which is soft and one that is hard. So they classify within the same hardness. And then in the bottom, they're showing that if you get the hard and soft of each shape, you can classify between those well. And just to explain the different colors, it's weird how they kind of show it with the legends at the bottom right. But basically what they're showing here, the green is the one that's the best, and they're showing that basically your FA encoding is the one that gives you the best classification. Your SA encoding, and I think frames per second, basically how often they're sampling the SA, basically is not as good in the initial time period because it has, this limited sampling rate, but the asynchronous gets you really quickly to good classification rates in terms of time after contact. So
I think the worst one was the hard versus soft, just the same shape, right?
which one? DEF or DEF as a whole?
Well, E seems to be the hardest because it plateaus to less than 100, but everything else seems to plateau.
Yeah. And I mean, these are good results, but also this is not the most difficult of problems. I mean, each of these classifications, right, like B and C, your random error, your random rate is 33% and DEF is 50%. So like in F, you actually don't get, with everything but green, you don't really get much above 50% until you get to like, what is it, like 80 milliseconds or so. Right, like there's that little bump and then it kind of.
Which makes sense because there's a slow adapting.
Yeah. So. Yeah, so this is another example. So those are kind of different toy applications or toy demonstrations that they did. And then they had a couple more demonstrations that are more related to illustrating certain properties, right? And so this is kind of cool. So we've talked so far generally about these sensors all being on one conductor, but you can imagine, and again, the traditional way is that you create some sort of grid. But when your only requirement is that your sensor is connected to the conductor, then you can create, whatever shapes you want. And so here they have these FA receptors that have their own power. So literally all they need to do is, they have a conductive output, they have an output with, some wire, and once it sits on the fabric, you got a connection there. So you can really just place them on the fabric and create any arbitrary sensing shape you want, right? So they have like the S shape, I don't know what that is, the second one's 0 or 6 or something, a smiley face. And then they're overlaying these rods on them and showing that, you get the output spike signatures that you expect, right? So in the left one, you're seeing activity on 3, 5, 7, as you'd expect. And so each of them has their own signature, but given that signature, you can place them in any way. Now, the practicality of that is I mean, it is very useful to have that. You wouldn't want to dynamically reconfigure your sensors like this, because obviously if you want to learn something about the world, you need to know where the sensors are relative to one another and all that. But from a design perspective, this is obviously very useful. And then the other example is damage resilience. And so on the top, they're showing their design, and the bottom, they're showing the traditional grid array. So we can start with the bottom, actually. So with the grid array, basically you have, I think it's a 4x4, and they place this whatever coin or something on the sensor array, and you get those readings of the pressure map on the top. But if you cut it, it has 3 lines for cuts. What happens, right, is that you are losing a bunch of the readings from the sensor. And that's because you're cutting through the traces, and so now certain sensing elements are not connected to the wire, the row or column wire that goes to your sensor or to your encoding system, right? And so they're showing when you cut this, you're losing information from your sensors, whereas you show on the top, right, they do those same exact cuts in their conductive fabric, but as long as the sensor has one path through the conductor to get to the final point, it's okay, right? Obviously, these cuts are convenient, right? Like if you did a cut, if you cut and you completely isolate it, there's nothing you can do about it. But as long as there's some route through the conductor from your receptor to the final decoder, then there's no effect on your movements. So this is showing damage resilience. So yeah, so I think a couple other thoughts that they brought up related to, so this is good, damage resilience is good because you don't want it to be that a few of your sensors die and it messes up everything else. It could be interesting. There are these ideas of like self-healing e-skins. So what if you were noticing that you haven't gotten a reading from a sensor in a while and you were able to like fix that part of the sensor? These are kind of more out there ideas that like there's a lot of kind of details in terms of how you actually do it. Those are some of the ideas. These are kind of demos. These videos are actually just demonstration of the last thing I showed you. So this is showing you the grid array. And actually, it's really hard to see on the phone screen the reading, but they're basically showing that, we press it, we get these sensor readings, then they're going to cut it, and they're going to show the fields. So I don't think it's like too.
This is a classic one.
This is the classic one.
Yeah, it's not rocket science.
Yeah, so I don't think there's really that much to like see that you guys don't understand. But, that's one, and then they do the same thing. So this is an example of their array, where basically each receptor is connected to all of its neighbors. So as long as has one connection remaining to its neighbors, it'll be fine. And here it's interesting that they're showing you the pulse signatures, not the like analog recording. That in contrast to the previous one. So I think that's really it. So yeah, I think the main takeaway from the paper is that they came up with a system. The hardware for it is really, really straightforward. Nothing that super complex there for us. It's all in the architecture. It all has to do with kind of making assumptions about how much activity you have, and then you get a lot of like nice applications that they showed off with their sensors. So I think it's very, again, I haven't seen anything much better than this in the e-skins world. But I mean, I probably don't know everything that's happening, but this is the best I've seen from an architectural standpoint. And it can support theoretically full body e-skins, which is definitely a goal that we want to get to for humanoid robotic systems or prostheses. We definitely want to get to thousands or maybe tens of thousands of tactile sensing units in the body. So that's it. I don't know if there are other questions or discussions.
Are the sensors here, is this the actual size that they've been using?
Yeah, so they talk about it a little bit. So in their sensor, actually, they have it in their supplementary material, the actual materials for the sensor itself. But it turns out, I think in their case, that the limiting factor size-wise was a microcontroller. That's one downside of this, is that they have to have a microcontroller for every sensor. And so the units that they had, which is still pretty small, they were doing like 3 mm by 3 mm for each sensing receptor. Or whatever. So still pretty good.
Yeah, smaller than this, right? Because this one's so large to be
Yeah.
like applicable for
Yeah.
different pieces.
Yeah, this is definitely on the larger side. So that's the smallest they did, 3 by 3, but again. I think they made an argument in there that you can do some sort of ASIC. And you can get much smaller than 3 by 3 for each sensing node.
How would you like give each one a different signature if you were to like miniaturize them to like a thing that's not a microcontroller?
Oh, I think it would still be some sort of microcontroller. But it would just be like the minimum microcontroller that you need, that you design yourself to like do what you need, as opposed to getting off the shelf. So I think that's, you still need some sort of compute. Yeah. You could, you could come up with some way to turn this all into analog hardware, and then you figure out a way to program the sensor, or like some sort of bit fusing or something like that to give the signatures, but I have a problem with it.
See, this is to be used for prosthetics. So the objective would be to give the output of the system through the brain directly.
I think that's one application of this. I would say that though that for this group, their application is mostly just for large scale robotic experiments. So I think the Python coding and all that stuff, that's just biological inspiration, but it's not, they're not trying to be like have fidelity to true biological signals or feedback. So that's something I'm more interested in, as you know, is how to create signals that are more matching biology and use that for feedback. I think for them, that's not what they're worried about. They're worried about how can I create a sensing system, high resolution, low latency, with many sensing nodes, very scalable.
And if you're saying this is biologically inspired, for our sensory neurons, we have individual axons going into the DRG, right? Like we don't have it's not combining the signal on the tip of my fingers and sending one wire to my spinal cord, right?
Yes and no. So you do, your afferents do combine signals from multiple receptors, but you're right in that you have many afferents in your fiber direction. So I think, yeah, they're very loosely saying, we're packaging it all in this fiber bundle, just like you're packaging it all in this, in an op amp, and then you're decoding afterwards. So it's very loose now, I think that.
Microcontroller that looks like they're using, and they're using a single microcontroller for each sensor.
Right.
I mean, it's not like terribly beefy, but like that's a single, like if for their processing, they're using the 18
tiny.
Yeah, 18 tiny. I don't know if it's correct for them to call it scalable.
Yeah, so you should have a discussion. There's someone in my lab, Eric Slepian, who this is actually the research work that he wants to do, which he that's what he said. He got this paper and he loved it's a really good paper, but then he was like, yeah, but there's all these microcontrollers and hardware. So if you look at the supplementary section, they have a whole board which is taking the readings from the sensor and then doing the decoding. So he's like, how can we get rid of the microcontroller and do this with like very simple passive components or whatever.
Yeah.
So I think that is a fair criticism for sure.
Very interesting. I'm not.
No, yeah, I'm not going to take it seriously. I mean, I still think, I think for me, it's more, what I like about the paper is how they think about things architecturally, rather than about like, the key to doing this is getting better fabrication, better, node process technology, smaller transistors and make things faster. It's like really just about how you organize the information flow, and the architecture rather than, making the devices themselves better, which I think is, and it's very simple. Yes. So. Cool. All right. Well, then that is it. Let me